Hi there, my name's Augie, and today we're going to be going over proofs. More specifically, we're going to do a proof by contradiction. Now, I love proofs by contradiction because they really help us understand what a mathematical proof is structurally. And it's also generally a more formally easier mathematical technique than the, frankly, much more frustrating for me, proof by induction. So, let's use proof by contradiction. Now, if you're new to proofs, all you'll need to solve this proof are the following things. Number one, some arithmetic. Number two, some algebra. And number three, a few definitions that I'm going to give you. So, here, we want to prove that the square root of 3 is an irrational number. Now, how are we going to do this? First thing we're going to do is we're going to ask ourselves, we're just going to remind ourselves what a rational number is. And if we recall, a rational number just means that a number can be expressed as a ratio of two different numbers. So for instance, the number pi is famously irrational because, well, we can't express it as a ratio. 3.141596, etc. Point is, that just keeps going forever. And we're trying to prove that the square root of 3, like pi, is irrational. In other words, we can't put like one number over another number and have that equal the square root of 3. So with a proof by contradiction, what we're going to do is we're going to assume the exact opposite. We're going to assume that we can find two numbers such that the square root of 3 equals them. So let's go ahead and let's pick two arbitrary numbers here. We're going to use, not the eraser, we're going to use this. So the square root of 3, if it is rational, we can write it as a over b, where a and b, just so we know, we're going to write a little bit of notation here. A and b are elements, that's that little e there, of the set of integers, which we write as z. In other words, a and b, it's not going to be like a can't equal something like 1.2, b can't equal 3.175. They've both got to be integers. You know, -2, 0, 38, 1, 2. So the first thing is they both have to be integers. And the second thing is that they can't have a GCD, a greatest common divisor, of anything greater than 1. So we write that like this, and I'll explain why in a moment. GCD of A and B equals 1. So if they have this property, this attribute, the GCD of A and B, that means they're co-prime. So for instance, just as a little bit of an aside here, if I gave you the following two numbers, 6 and 3, we can see that their GCD isn't 1. They're not co-prime. You can divide both numbers by 3. Now if we do so, we get 2 and 1. Now 2 and 1, that GCD is 1. 1 is the only number that goes into both. Let's look at another one here. 17 and 5. Well, 17 and 5 are both prime numbers, so we know that their GCD equals 1. Another one is 8 and 6 is not a set that has a GCD of 1 because we can divide both sides by 2. Doing so gives us 4 and 3, but 4 and 3 are co-prime. Alright, so hopefully you have a little bit of an idea of what we're looking for. We're looking for two numbers that we can express one over the other as a ratio, hence the term rational number, and they have to be co-prime. And there's one other little thing that my old professor would kill me if I didn't mention this, because it's something that people tend to take for granted in mathematics, and that is, very importantly, write it here, b cannot equal 0. Because remember, we have a over b, can never divide by 0. It's like a really bad thing, and a popular internet meme is made off of it. So, b can't equal 0, the GCD of a and b has to equal 1, and a and b are both integers. Okay, so if we're assuming that, what can we do? Well, this is where you get a little bit creative with your proofs. And one of the fun things about proofs is that once you see something once, you start to gain these little techniques that you can do. One thing that I know is that I don't really like having radicals if I can help it. So what I'm going to do is I'm going to go ahead and I'm going to get rid of that radical. And I'm going to do that very simply by squaring both sides. So we're going to go ahead and square the square root of 3, and we're going to square a over b. And in so doing, we're going to get 3, because remember, the square root of 3 squared is just the number. So the number is 3 equals a squared over b squared. Well, that's interesting to see, but it doesn't really help us. So let's try something else. Let's get both variables on opposite sides of the equal sign. And we're going to do that by cross multiplying. So we're going to get 3b squared. See, I'm multiplying the denominator over here times the numerator, 3 over 1. And 1 times a squared. And we get 3b squared equals a squared. Okay. Now you might see something here that is a little bit weird. I mean, I certainly see something here that's a little bit weird. I can see that a squared, if we look at this, let's rewrite it so that it's a little bit more clear. Let's look at a squared can be written as 3, the number 3 times b squared. Now, there's a very important property that I'm going to show you. You can prove this, and you probably, even without knowing it, have the skills to prove this. But for a and x, if you have two numbers, a and x, and they're both integers, if a divides x squared, this is very important, if a divides x squared, a also divides x. All right, so how does that help us? Well, if 3, in this case, if 3 divides a squared, then it follows that 3 divides a. So what does that mean? Well, that means that a is a multiple of 3. Okay, so we know that. Now, or a can be expressed as 3 times some other number. Okay, well, if we know that, let's write it as such. So in this case, if we can write a as 3 times some number, let's call some number k. So k, like a and b, is going to be an integer. All right, so let's write it. A equals 3 times k. All right, so if that's true, then we can take this a and plug it right back into the a squared. And if we do that, we get 3b squared equals 3k squared, or 3b squared equals 9k squared. Or, if we divide now by 3 on both sides, we get b squared equals 3k squared. Okay, now, if you're looking at this, you'll see a striking similarity between the previous proof with a. Because now, with the exact same knowledge that we have here, I'll write it out explicitly so that you can see it, we've got b squared can be expressed as 3 times some number k. So that means that 3 divides b. And you may realize it, or you may not, but at this moment, we're done. We're done, because 3 divides a, and 3 divides b. But part of our assumption, if the square root of 3 is a rational number, that we can express a over b such that they have no common divisor of higher than 1. But, in fact, the GCD of A and B is at least greater than or equal to 3. And then we just write the beautiful word contradiction. And that indicates that we're done. We've proven that the square root of 3 must be an irrational number, because the conditions for rationality that we previously expressed were violated when we realized that the GCD of A and B was higher than 1. And that is how we do a proof by contradiction. There are so many really exciting proofs. This is one of the more famous proofs. But I think it's a great place to start. And if you need some help in number theory or advanced mathematics or anything having to do with proofs, or you're just curious, I recommend you work with one of our tremendous tutors at Chegg Tutors. And I hope to see you later. My name's Augie. Take care.